So, let us start this lecture with a new section on matrices. In this section I want to establish many assertions on the representing a matrix by as a product of simpler matrices, and also use this representation to compute inverse of a matrix in a simpler way over a field. And then I will also at the last I will also say something about the matrices with integer entries and use this to in a theory of abelian groups to establish a structure theorem for finitely generated abelian groups. So, this may happen in this lecture and next lecture also. So, let us start defining. So, this is a section on elementary matrices. So, let us first recalling, or I want to set up some notation which I will use it again and again all the time. So, suppose we have a matrix A, numbered rows are numbered by I and columns are numbered by j, and this is a matrix MnK. So, I is varying in the set 1 to m and j is varying in the set 1 to n. We will say it a diagonal matrix. A is called diagonal if all indices Aij are 0 for all Ij in I in the set 1 to m, j in the set 1 to n, and I not equal to j. It may not be a square matrix. So, for example, and this I will denote it by, and if you put k is the minimum, m and n, this matrix I will denote, the diagonal matrix I will denote by d I a g dag, that is a short form for the diagonal, and a1 to ak. So, it will look like this. It will depend whether the m is smaller or m is bigger. So, a1 to ak and the remaining guys are 0. In this case the number of columns are more. This is the case where n is bigger than m. Similarly, you can write the other case. It will be like this. Then there will be more 0 0. So, such a matrix is called a diagonal matrix. Square matrix is diagonal if it is the m equal to n and all other entries are. So, this is called a diagonal matrix, and in this case also I will here I should have put a1 1 etc., but in the case diagonal case only aii entries are non-zero, possibly non-zero, and these entries are usually denoted by ai. This is I is from 1 to k, where k is the minimum. All right. Let us see one example which will be useful when we do linear operators. Example. For example, if Vi is a basis, Vi I in I is a k basis of a k vector space. K vector space V then and f is a linear operator. F is a linear operator from V to V, K linear operator. Then the matrix of F with respect to the basis V. This is a square matrix, is a diagonal matrix. If and only if of Vi is a scalar multiple of Vi for all. This means, so that is each this Vi is an eigenvector of F. It keeps this one dimensional subspace spanned by Vi invariant under F, and this is what we will need. We want to decompose our vector space. Given a linear operator on a vector space, we want to decompose a vector space so that on each piece it will look like this. Okay. So another thing I want to mention here is the diagonal matrix. When is it invertible? That is, diagonal matrix. Let us take a square matrix. Diagonal matrix AI, I in I. This means a diagonal on the diagonal entries are given AI. So A1 to AN, remaining entries are 0. This is square matrix. Is invertible. If and only if all AIs are non-zero. And in this case, the inverse is very easy to write down without any calculation. Diag AI I in I, inverse of this is also diagonal matrix with the diagonal entries inverses of the elements AI. So this is very easy. Similarly, I want to define triangular matrices. So triangular matrices are of two types: lower triangular, upper triangular. Upper triangular. And given a matrix, there is a main diagonal. This is a main diagonal that can either be like this when the number of columns are more, or it can be also like this. See, this is rows are more, this is columns are more. So this is called a main diagonal of a matrix. This can be either this or this depending on who is more. In the case of equal, that is the usual diagonal. And lower triangular means this upper part is 0 and down is some stars. These elements are some elements in the field. Upper part is 0 above the main diagonal. And upper means upper part is arbitrary elements, could be 0, may not be 0, and the down elements are 0. This is upper triangular, this is lower triangular. In case of a matrix who is a square matrix, a triangular matrix, very easy to find whether it is invertible or not. We would have seen in earlier assignments also that if the main diagonal entries are non-zero, then it is invertible, and inverse we need to compute. So, we will address this question of computing inverse little soon. Okay. So, that is again I want to first write one example in terms of the matrix of a linear operator, and in addition to these matrices, diagonal, triangular, and I will define another special type of matrices, and our aim is to prove that every matrix can be written as a product of these matrices. Okay, so let us write one example. So, suppose we have a V is an n dimensional vector space, V is k vector space of dimension n, and V1 to Vn is a basis. And suppose we have a linear map F, V to W, V to V, and let us put capital Vi is a subspace spanned by V1 to Vi, KVI. This is from I equal to 1 to n. So, we have a chain of subspaces V1 which is generated by V1, then V2 which is generated by V1, V2, and so on, Vn. This is the whole vector space V, and at each stage they are proper, and before this there is a trivial vector space V0 which is a singleton 0, and each time dimension is up more because this is a part of a basis. So, dimension of the subspace Vi is precisely I. In fact, V1 to Vi is the basis of Vi. So, this is a ascending chain of subspaces. It is also called a flag. Remember, this is a flag in V. So, when will the question is now, when will the matrix of V or matrix of F with respect to the basis V is upper triangular. That means what do we need? We need, see this matrix, this matrix is, if you call it Aij, Ij are in, they are in 1 to n, the square matrix, and this is defined, these Aij's are defined by this equation. For any j from 1 to n, f of Vj is the sum Aij Vi, I is from 1 to n. These are sort of n defining equations of this matrix, and this f of Vj we are writing it as a jth column, and we want upper triangular. So, that means below the diagonal all the entries in the jth column should be 0. So, that means below means the row number should be more than the column number. So, that means the condition is, this is if and only if Aij are 0 for all I strictly bigger than j, because when you write it in the column below the main diagonal they will be 0. But this condition you can nicely put it, that is equivalent to saying, for each I in 1 to n, the subspace Vi is invariant under F. because if it is so, then when you write, let me write the index j. For example, f1, f of v1 should be contained in v1. This means f of small v1 I should be able to write in terms of v1 only, that is a11 v1. The remaining coefficients are 0. F of v2 should be contained in v2. That means f of v1 and f of v2 both I should be able to write only in terms of v1 and v2. This is a21 v1 plus a22 v2 and so on. So, each Vj should be invariant under F. So, this condition is said as Vj are F invariant. So, it is in general it is an interesting problem. Given a linear operator, how do you decide there is the invariant subspace and what is the dimension and so on. This we will do it soon. Okay. So, the upper triangular matrices, upper triangular set of all upper triangular matrices I will denote by U N K. This is square matrices only. So, this is upper triangular square matrices. So, this is a subset of M N K. And not only subset, note that if you add the two upper triangular, you get upper triangular. If you make a scalar multiple, it is upper triangular again. Also, if you multiply two upper triangular matrices, you get upper triangular matrices. So, that simply means that this UNK is a K subalgebra of MNK. So, also we would look for an operator. How do we decide the matrix of a linear operator is upper triangular in general. And once we said upper triangular, similar thing we can do it for lower triangular. So, LNK, this is lower triangular matrices, that is also subalgebra of MNK. Okay, so continuing this example little bit, let me study now what are so called nilpotent operators. So, this next example, nilpotent operators. So, V is finite dimensional. We will put n in the dimension of V. And in this I want to characterize nilpotent operator. So, what does one mean by nilpotent operator? So, if F is an operator, that means an element of this K algebra, we will say it F is called nilpotent. If F power some power F m is 0 for some m. So, this is a composition of F m times. This is F compose F m times. Soon I will give example, it will be clear many examples after the characterization. This concept of nilpotent elements makes sense in any K algebra. If you have a K algebra, or for that matter if you have any ring, then an element is called nilpotent if some power of that element is 0. Okay. And the smallest power where it is vanishing, that is called the degree of nilpotency. Degree of nilpotency. That means f power m is 0, but not the earlier one. F power m minus 1 is not 0. Then m is called the degree of nilpotency. Okay. So now I want to write equivalent statement so that we can show this. The following are equivalent. This is easy or different way to test when operator is nilpotent. 1, f is nilpotent. 2, f power n is 0. This is n is the dimension of V. So that is the degree of nilpotency of f is smaller or equal to n. It could be 0 earlier, but definitely at n it becomes 0. Third, there exists a flag flag means 0 equal to V0, V1 is Vn equal to V in V such that f of Vi is not only contained in Vi, it is even contained in the earlier one. This is contained in Vi minus 1 for all I from 1 to n. This is the third condition. And fourth condition, I will have to write in the next page unfortunately. Fourth condition, there exists a basis V1 to Vn in V such that the matrix MV V F is upper triangular with diagonal with all diagonal entries 0. That means it looks like this: 0 on the diagonal, below also 0, and somebody is up. So, proof. One implies 2 implies 3 by induction. So, let me indicate the proof, and then I will indicate 3 implies 4. First, let us prove this. So, let us assume dimension is positive, because if dimension is 0, there is nothing to prove. And assume f, assume 1, that is f is nilpotent. 1 is f is nilpotent. Then first note that f cannot be automorphism. F is not automorphism. Because f is automorphism and f is nilpotent, I will keep cancelling 1 by 1 f. So f cannot be an automorphism. That means, and we are in a finite dimensional case. So therefore, and Hence, F cannot be unsurjective. Because on a finite dimensional surjective linear operator is also bijective. So, F is not even surjective. Okay, now let us, and what do you want to prove? We want to prove 2. So, let me show you the 2. 2 is the degree of nilpotency is less than equal to n, and 3 is there is a flag. So, I am trying to construct a flag. So, Vn, you put Vn equal to V. And Vn minus 1 arbitrary one codimensional subspace, K subspace of V. Which contain image of F. See, image of F is a subspace of V equal to Vn. This is not full. So, the dimension, because it is not surjective, so the dimension of this should be smaller. So, I am saying choose Vn minus 1, so that the dimension this is 1 and which contains this is possible. This may have dimension n minus 2, in that case I will enlarge it by one more dimension and so on. So, choose that. Then I want to then Vn minus 1 is invariant under F. Because F of Vn minus 1 is actually contained in F of Vn, which is the image of F, and we have chosen this, so that this is contained there. So, this is trivial. So, that is Vn minus 1 is F invariant. And now, because it is invariant, I can look at the restriction of F to Vn minus 1. This is an operator from Vn minus 1 to the vector space Vn minus 1, and the dimension dropped by 1, and the nilpotency is still varied. This is nilpotent. F restricted to Vn minus 1 is also nilpotent. So, therefore by induction, this is on n minus 1 dimensional vector space, this is linear operator nilpotent. So, the 2 for this will be this power n minus 1 is already 0 by induction. And from here I say, from here it follows that F power n is 0. And then you keep doing by induction. So, this is a little thing to check, that if this is 0, then this is also 0. Okay. So, now I then complete the proof by induction. So, this proved 2, and in 3 also we wanted to prove, but 3 also I was trying to prove simultaneously. I constructed Vn minus 1. Now, I will forget original V and original F and work with this and keep doing the construction of the flag downwards. Now, 3 implies 4. 3 says there is a flag of invariant subspaces, and 4 says there is a basis which the matrix of F with respect to that basis is upper triangular with a diagonal entry 0. So, we have given a flag, so I choose a basis for the flag. So, that means I choose V1 to Vn in V such that for each I 1 to n Vi, this has this basis k V1 plus k Vi. This must be the basis of Vi, and because f of Vj is contained in Vj minus 1, that is given this is the property n3, this is given. So, therefore, f of Vj in particular should be an element here. So, that means we should be able to write it as this is the summation Ai j, and I will run only from 1 to j minus 1 Vi. So, that means the jth column of the matrix with respect to the basis V will not contain, including the main diagonal, nobody down. So, this is the jth column f of Vj. So, here entries will come up to, this is the j minus 1th row, and this is jth row, which is 0. There is no coefficient of Vj in this, and below also nobody. So, this is 0. So, and then something might be here. So, that means the matrix of F will look like this, diagonals 0 and somebody up. So, that is it's a lower triangular upper triangular matrix with main diagonal 0, that is precisely was a 4. Okay. So, now we can also prove 4 implies 3, that is not so difficult, and 3 implies 2 also you can prove. These are all simple. So, just verify them. So, that gives a big motivation for studying triangular matrices, upper, lower, also the diagonal matrices. And in addition to that, now I want to introduce matrices which will come from elementary row and column operations. This we do it after the half.